Assalamualaikum. Assalamualaikum. Good morning.
Waalaikumsalam.
Waalaikumsalam, Doktor. Good morning.
Okey, ada 2 orang lagi belum masuk. Kita tengok siapa dia yang belum masuk lagi. Ni Hafiz, ada Hafiz, Haziq. Haziq ya? Hafiz. Ada lagi. Siapa yang ada nama 2 tu, Hafiz ya?
Haziq. Haziq.
Haziq. Satu lagi Haziq tak ada. Okey, lagi seorang. Hasif yang tu. Okey, Mani Sufi. Seorang tak ada. Okey. Dia tahu tak ada kelas hari ni? Patut tahu kan? Sekejap je saya buat kelas. Lepas ni awak pergilah mana-mana nak pergi pun. Awak nak pergi shopping ke, IOI ke? Amirun ada? Amirun. Aduh. Okay. So, can we start now?
Yes, Doktor.
Syamimi ada? Syamimi tak ada? Irdina ada? Irdina?
Ada, Doktor.
Okay. Okay, so our test will be next week lah. They want it on the 18th. Yeah, Friday night. Most probably on Friday night. Okay, so let me check. Siapa baru masuk? Ada lagi seorang. Ada seorang lagi belum masuk. Siapa belum masuk? Okay, ni can you see the slide? Okay. Kenapa saya tak dengar suara ni? Siapa tak start ni? Awak ingat tak dekat mana kita stop? Where did we stop last time? Last week. Ni dah ke? Ini dah Ni dah. Ini sudah, ni sudah. Ni dah belum?
Dah, Doktor.
Ini dah Ini dah Ini dah, okey. Ni pun sudah. Ni dah kan? Parallel in, serial out. Okey.
Belum.
Ini belum? Ini dah? Ini sudah kan?
Yang waveform sudah, yang bawah tu belum.
Okey. Okay, so continue here. Okay, so today we continue with parallel in, serial out, shift register. So shift registers can be used to convert parallel data to serial form. Okay, there are several types, right? Several types of shift register. There's serial in, serial out, parallel in, serial out, and so on. So this is one of the form. There is parallel in, serial out. Shift registers can be used to convert parallel data to serial form. The logic form for this type of logic diagram for this type of register is shown. Okay. This is for 4-bit parallel in, serial out. So when you have 4 bits, you have here 4 flip-flops. Yeah, remember that. So this part is the input. Okay, parallel in. You have here D0, D1, D2, and D3. And then look at this part here, label as shift and load. Okay, if you look at here, load, you have bar. So meaning when the signal is low, the data will be loaded into this circuit. Okay, at this input. Okay. When the signal is high here, okay, then it will start to shift. So you must know what is this shift and load. Okay. So when high, it will shift. When it is low, it will load. Okay, the data will be loaded into this circuit here. Okay, and then this is the clock. So there is no bubble, meaning this is positive, active. Positive? Look at the positive edge. Okay, there is no bubble. If there is a bubble, then it will be a negative edge. Okay, and then the data will come up at this port here, at the last one, that is at Q3, serial data out. So you can look at this symbol. This is for the parallel in, serial out. So you can see here the data is D0, D1, D2, and D3 here. And then data out here is Q3. And you look at here, this shift and load, yeah. Okay, so when it is high, it will shift. When it is low, it will load. So you have low here. Okay, this is the part where the signal will be loaded inside this IC here. Okay, so you look at the waveform. Okay, so when this is low, it will load into here, and then this part is high, so it will shift. Okay, it will shift here. So you have here, this is the last bit, last bit D0 here. 1, 0, 1, 0. Okay, now the same circuit here. The circuit uses D flip-flops and NAND gate. You can see here all the NAND gates for entering data to the register. So D0 or D0, D1, D2, and D3 are the parallel inputs. Okay, these are the parallel inputs, where D0 is the most significant bit. Okay, now here D0 is the most significant bit and D3 is the least significant bit. To write data in, the mode control line is taken to low and the data is clocked in. The data can be shifted when the mode control line is high. Okay, why? Because look at here, there is no bar on shift. So meaning here, look at here, the data in, okay, the write data in, to write data in, the mode control line is taken to low. Okay, so you have bar here, right? And the line is high as shift is active high. Okay, so at shift here, there is no bar on the shift here, so meaning it's high. It is high to shift, yeah? So the register performs write shift operation on the application of a clock pulse as shown in the animation below. So now you look at here. Look at the animation. So this data goes in and then shift goes up one by one. Right? Can you see that? Okay, clear first. And then right, data goes in and then it will be out. Can you see? At the bottom here, bottom of the circuit here. Okay. Okay, now look at this here, 74HC165 shift register. It is a CMOS 8-bit parallel. Okay, parallel in, and then serial out shift register. The logic symbol is shown, so you can see here the data in from D0 until D7. This is for 8-bit, and here is the data out Q7 here. Okay, so you see here you have SA here, meaning for shift. That is for because you don't have bar on top here, so this is active high for shift, and then load here. This is serial in. Okay, here clock inhibit here, inhibit, and then clock here. Okay, the clock CLK and the clock inhibit, that is clock I and H lines are connected to a common or gate. So either of these inputs can be used as an active low clock, enabled with the other as the clock input. So data is loaded asynchronously when shift and load is low. Okay, here mentioned here data is loaded when it is low, and move through the register synchronously when shift load here. Okay, that is referred to shift is high and a rising clock pulse occurs. Okay, so now this is another full circuit here. You see here 8-bit parallel shift register. So you have here serial in, you can use for serial in. Okay, this part is the shift and load. And then you have also clock, this is parallel input, and then you have the output taken here. This is the whole circuit. Okay, if you look at here, this is only one IC here, this symbol. This is what inside in the IC. Okay, you can imagine, you have here D flip-flop inside here. So this is the IC. Yeah. Serial. Okay, I think you can use this for serial in also, this IC. Okay. Okay, so this is the whole waveform. You can see on the top here, this is the clock, and then you have clock inhibit, you have serial in. This is always low because if you look at here, this here, okay, serial here, you have here, but here is cancel up because this is inverter. This is inverter, so you have bubble here, so this is cancel out. Okay, but mention that serial always 0 here. Anyway, you don't have to memorize all this because for the function of the IC, you must refer to the spec. For example, for this one, this serial. But this one is important to know. Shift and load. When it is low, it will load. And SA here refer to shift. It will shift. So shift when it is high, for example here, you look at this waveform, this is low when all the data is low. So you have the data here. Okay, 1 0 1 0 1 0 1 1. Okay, this is all the data. It will be load into the IC simultaneously because this is in parallel, right? And then this part is high. So this is where the data will be shift. So it will shift, okay, to the right here. So if you look at here, this is the data, and then it will be load here. Okay, then you have here 1 0, see 1 0 1 0 1 0 1 1. Okay, we shift at this part. This is look at here, this is clock inhibit. Okay, so at this part it mentioned here inhibit. look at here. This part, because this is low. Okay, we start to load. So the data will load inside the IC. But this part is inhibit. Look at this symbol here. Inhibit. Where is clock inhibit here? Okay. So this part inhibit. So nothing happen yet. It's okay until when the inhibit is low here. Okay. And also look at the signal here. This is high, so it will start to shift. So then it will shift. Okay, serial shift. So just now one goes in, 1 0 1 0 1 0 1 1. So we shift. Okay. Okay, now this is parallel in, parallel out shift register. Okay, this is 4 bits, because you have 4 flip-flops. So all the data at the top here, the input, and the output is taken at the queue. So you have here key 0 until Q3. This is parallel data out, yeah? And then look at the clock here. You don't have any bubble, so you refer to the positive edge, yeah? Okay. This is synchronous or asynchronous? Okay. This is synchronous, yeah, because you have only one clock connected to all. Okay, this is synchronous shift register. Okay. Okay, now this slide you look at here. This is 74AC195 4-bit parallel shift register. Okay, so you have here on top here all the parallel data in, and then at the bottom here, this is all the data out. This is parallel data out. So here you look at here using JK flip-flop because it's labeled here JK. So this inside IC, meaning it uses JK flip-flop. And then you have shift and load. You have clear and then you have clock here. Okay. So now look at this part. Okay, clear you have bar or active low because you have bubble here. So when it is low here, okay, it will clear, and then here is the JK flip flop. Okay, so this is serial input, but when we are referring to parallel input, so we refer here, okay. And then you have here shift and load, and then this is the data input. Okay. So you look at the waveform for shift and load here. So you have here high, and then you have low, and then you have high. Okay, so this part both are high. Okay. Okay, look at here. This is clear. Okay, both are high because when you look at this waveform, you must look at all part here. The important part is here. You must refer to here, all this part here. Okay, now you must look at one by one. Clock, positive edge because you have no bubble. So you refer to the positive edge. And then you have clear. Okay, you must refer to the negative here. This part will be clear. And then you look at here, shift and load. When it is low, it will load. When it's high, we shift. So here, this is high, we shift. And then this part will load. Okay. Now, then you look at here. What happened here? JK is both are high. Okay, both are high. So now, if you have data here, okay, you have data here, goes in here. Okay, so at this part when both are high, okay, this is serial shift. It becomes serial shift. Okay. So since anyway you look at here, because this is high also, so it will shift here. Okay. The data is what? The data is, look at here. This is J, K. Okay, this is the data out here. Okay, so both are high here. The data is here is 1010. Okay, so this is the data here, serial shift, but this is the real data when you load it, because you load the data at here because you want to use the parallel in here. So you have here 1010. So 1 here, okay, 0 here, 1 here, 0 here. So here it will shift. Okay, see, it will shift here. So this is the data that you have in the input just now. Okay. Okay, now here is 74HC165 shift register. This using the multi-sim, I guess. Okay. You can design this multi-sim simulation of the 74165A is shown. The word generator is used as a source for the pattern shown in the green probes here. Okay, so you see the green probe here. So it goes inside here, and then you can design this in the lab. Okay, this is more significant bit. Okay, pattern is loaded when J1 is low. Okay. Okay, now you can see this is the most significant bit. Okay, and then this is the data comes out here, and then this is when it is low because the low. Okay, it will load. Okay, and then when it's high, it shift here. Okay, this is referred to clock and so on. Okay, now we go on to the bidirectional shift register basics. Okay, so ya, pergi sana dulu tak? Mama ada kelas.
No, mommy, I'm just seeing you.
Okay, bidirectional shift register, okay, we label is BSR, is one in which the data can be shifted either to the right or to the left. Okay, because it says here bidirectional, so it can move two ways here, so either to the right or to the left. Okay, so the BSR can be implemented by using logic that enables the transfer of a data bit from one stage to the next, okay, to the right or to the left. So BSR has a control line for selecting right or left shifting mode. Okay, so here the logic high, HI here, on the right and left. So you can see right and left normally in the IC written there. Control input allows the data bits inside the register to be shifted to the right. So when it is high, because right here you don't have bar, so meaning when it's high, it will shifted to the right. Okay. So a logic low when the right left here. Okay, so because left you have bar, so meaning this is low. Control input allows the data bit of the register to be shifted to the left. Okay, so when high, it shifted to the right. When low, shifted to the left. Okay, bidirectional shift register. 4-bit serial in, serial out. and also there's another one that is 4-bit universal. Okay, so now we look at here 4-bit serial in, serial out. Okay, so this is the function here, right and left. So you see here, right, when it is high, shift to the right. When it is low, shift to the left. Okay, so serial data in goes in here. Okay, and then from here, it goes to the next flip-flop here, and then it goes to the next Q2, and then go to Q3. So your output is taken at Q3. And then look at the clock also. There is no bubble. Okay, so this is active high. Any question? Okay, you will see, you will understand when you look at the waveform later on. Okay, I will explain that. Okay. Okay, now look at here. You can see here, right? Right, left. This is already written for you because when it is high, shift to the right. When it is low, shift to the left. Shift to the right, shift to the left. Okay, this is the clock. Okay, the clock is positive age. Okay. Okay, now look at here. Because this is serial in just now, right? Okay, so you have data. Let's say you start with 1. Is it serial in, for example? Okay, this one is serial. Okay. Okay, so let's see. For example, if Q0 here, you have 1, yeah? Start with 1. And then you shift to the right. Okay. And then here, wait. And then you have Q1. Start with 1. Q2, you have 0. And Q3, you have 1. Okay, so the data will be, let's say, the most significant bit is Q3. So 1, 0, 1, 1. Okay, now look at this part. This is shift to the right. So you see here Q0 here. This one goes to Q1. Shift to the right. Q1 here, the one here goes to Q2. Here. Can you see my cursor? Okay. And then you see Q2 is 0 here, right? So it goes to Q3. Okay. The top one just now, because you start with 1 here, so this one will be 0. So this is shift to the right. Okay. So this one goes to Q1. This one at Q1 here goes to Q2. This Q2, the 0 goes to Q3. Why? Because you look, you look at here. This is Q0 here, Q1, Q2, Q3. You look at here, this is connected to Q1. Q1 is connected to what? Goes to into the AND gate and then goes to OR gate Q2. And then Q2 is connected to Q3. So that's why just now if you see Q0 goes to Q1, here Q1 goes to Q2, Q2 goes to Q3. Okay, faham? Okay. And then you look at here. Then you have here 0, 1, 1, 0. So this 0 goes to Q1. This one goes to Q2. This one goes to Q3. So you have here 0, 0, 1, 1. And then again, look at here. So this part here, right? This is high. So shift to the right. Now at this point, at this clock here, this is already shift to the left. shift to the left at this point, yeah. You see my cursor here? This is already shift to the left. So now, shift to the left is going up. Okay, so you start from bottom here. Here you have 1 here, goes to Q2. 1 here goes to Q1. 0 here goes to Q0. Okay, so until at this clock here, this is still shift to the left. So this part just now, because this one goes here, so this one just now you make it low. Okay, this part will be low. So 0 here goes to Q2, 1 here goes to Q1 here, 1 here goes to Q0 here. So at this point, you see here, this clock still shift to the left. Okay, so 0 here goes to Q2, 0 here goes to Q1, 1 here goes to Q0. Until at this clock, shift to the right. Okay, shift to the right. Now here 1 go to here, Q0 goes to Q1, Q1 goes to Q2, Q2 goes to Q3. At this clock, this shift to the right, and then it going this way, this way, this way, until this clock, this shift to the left. Okay, this shift to the left going up. Going here, going here, going here. This part you must make it 0. Okay, and then shift to the left at this point. So going up, going up, going up. And then this is 0. Okay, so you stop here. Okay, faham tak? Aha. Aha. One dia hilang yang mana? At this point. You mean dekat sini ke? Sini ke? Okay. Ni pergi sini. So yang ni become 0 lah here. Okay. Okay, so advanced shift register application. Okay, serial to parallel converter. Serial to parallel converters are the digital circuit used to provide the data transmission conversion within the computer. Okay, so you can see, okay, this serial to parallel converter, you can see serial data in. Okay, so you have here data in input register, and then you have here also data input register. This is in parallel output, yeah. Serial in, parallel output, and then goes to another register, parallel out. And then you also have here what? Counter, right? Counter divide by 8 here. You have this clock, you have JK flip-flop and so on. This is okay, parallel to a serial to parallel converter, yeah. This is big circuit here. And then serial data format. Okay. Aduh. Penat explain this one. Okay, you have here data. D0 until D7. You have start bit here. You have stop bit. Why do you need stop bit? Because you don't want to mix with the previous data or the next data. So you must have a stop bit, eh? Okay, so here serial data in, you have here all the data inside here, and then you have control flip-flop. Okay, you have clock here. This is positive edge because you look at here at the positive edge here. And then here, data input register. Okay, so now look at here. Okay, you have here at 1 clock here, you have data input here, 1, and then you have 0, you have 0, you have 1, you have 1, you have 0, you have 1, you have 0. Okay, so this is serial data, right? So serial data, it goes in, and then it will go to this part first, and then we shift until to the end. Okay, and then at the output, you will get back the data. Okay, you take the clock when you take the data at the end of the clock, right? Because here you have 8 bit, right? 1, 2, 3, 4, 5, 6, 7, Okay, so after that. Okay, clear? Okay. Load data out register, so you get back the data. You take the data at the after the 8 ya. 1, 2, 3, 4, 5, 6, 7. Okay. Then you take the data. Okay? Okay, this is the bidirectional shift register. Okay, you can either shift to the right, to the left. Okay, so logic analyzer simulation shows a bidirectional shift register such as the one shown in figure below here. So notice that the high level from the serial data in is shifted at first from Q3 towards Q0. Shifted from Q3 to Q0. Okay, so look at here. This is shift to the left, right? Shift to the left is going up, right? Remember? Okay, shift to the right is going down. Okay, now this is the serial data in. So you have this, start with this. You have, this is the data, and then going up, until here. Where is the clock? This is the clock, positive age, positive age, positive age. Okay, and then positive age here until here. This is still left. Okay, this one is already shift to the right. So it's going down, going down, going down, going down. Right? Okay. So now question, how will the pattern change if now right or left control signal is inverted? So what is the output like? Huh? No. It will invert lah. Okay, because the signal invert, dia pun jadi macam tu. Instead of tadi yang besar kat bawah kan? You see the waveform just now? Okay, see? Because it shifted to the right, to the left, and then to the right. Okay, now if the output is like this, the right and left here like this. Okay, shift the right foot and then left. So the output will be opposite of what you have just now. Okay? Okay. Another type shift register is the universal shift register. Okay. A universal shift register has both serial and parallel input and output capability. So the 74HC194 is an example of a 4-bit bidirectional shift register, a universal shift register. So you have this one. So you have more what? Here, more of the command here. Okay. This is 4-bit. So you have, you see here, SR. Can you see here, my cursor here? SR, SER here, SL. Okay, meaning here shift right serial, shift left serial. Okay? So this is clear. So this is S0, S1 serial. Sorry, shift right serial, shift left serial clock. And then this is the parallel input, and here you have the parallel output. Okay. So now, okay, this is the waveform. Aduh. Okay. Can you see this waveform? Okay. This is quite difficult to explain to you. Now look at the clock. This is positive age, right? And then you have control mode. Okay, mode control input. You have the first one is high, and then here you have high, low, and so on. And then you have clear. Okay. When it is low, it will clear inside here. Okay, then you have serial data input. You also have serial data input here. This is shift right, shift left. Okay. And then you have the data in parallel and the output here. Okay, so now look at here. This is the clock here. This is high. So of course, it will clear first and then it will load. Okay, it will load. Okay, so you have data high, low. Okay, so when this high, low, at this point it will load. Okay, so you will the next clock here, immediately the next clock you have the data in. That is high, low. Okay, see? And then what happened now? The following clock here. Okay, so you have here shift right. See, you have shift right. This you have serial in shift right. So it will shift to the right. So the data will be shifted. So the output is here, right? Just now, this load. So we shift. So this going there, is going there. Okay, this low going there and so on. This is until shift right here. Finish. Okay, and then it will start to shift left. Shift left is here. Okay, now this shift left, shift right here, this refer to this mode here. Control input here, mode control input here. Okay, so meaning when S1 is high, it will shift to the right, and then when S1 is high, it will be shift to the left. Okay, and then it will inhibit when it stop here. This is also stop. This also inhibit this part here. Okay, that's why then it start to shift to the left, and that will clear. So this you must refer to. You must refer to the spec here. What is S0 here? What is S1 here? Okay, and then what is this? This is for serial. If you use this part for data input, but now you use parallel, right? You will use parallel data input, so you must refer to S0 and S1. Okay, if you use this IC for serial data input, then you refer to this part. Okay. Okay. Okay, so now shift register counter. Shift register can form useful counters by recirculating a pattern of 0 and 1. Two important shift register counter are the Johnson counter and the ring counter. Okay, now. Okay. Here. Which one? This one? Shift to the right here. Become one balik, what do you mean? Dia macam, dia inhibit dekat sini tau. Okay, dia stop. Dia macam dekat sini. Okay. Okay, dia stop kat sini. Okay. Because they refer to this one. Then only they shift to the left. So, whatever here is maintained is here, right? And then it start here because it's going up. Okay, because shift left, right? Going up, right? So, this 0 going up here. Okay. So, and then 0 here goes up here, 0 here goes up here. So, here it become 1 here. Okay. Remember when it going up, then see here. Wait. I show you this one. Go back. Not this one. Okay. shift to the left. Okay. So here going up, going up, going up. Sorry, this is going right. Going down, going down. This part going to the right. Okay, so until here. So here is going shift to the left. Shift to the left. So this going up here, going up. And then we left here with 0. So then left here going up, going up, going up. Okay, we have 0. Okay. Okay, so you have here shift to the left. So shift to the left is here. So here is going up here, going up here, going up here. Okay, then you have, but here, it becomes 1 here. When it left, going, you don't have anything here. So it's going up here, going up here, going up here. Here becomes 0. Okay, so going up, going up, going up. Because this is left. Okay, inhibit here. Okay, so let me check. Okay, so the S naught, S0 here is mentioned here. S0 high, okay, this is S0 high, positive H clock, at the positive H clock, okay, and S1 low, okay, this is high, positive H clock, S1 low here, this is shift to the right. So when S0 is low, and S1 is high at this part here, then this will shift to the left. Here, here, shift right, serial here, okay, goes into Q0 here. This goes into Q0 stage, and SL, okay, shift left here, okay, goes to Q3 stage, okay, goes to Q3 stage. So you see here, this part here goes to Q3 stage. That's why you have here high. Okay. 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 So SR serial here, because this is all low, this part goes to serial right. So this part goes to the mention here, SR serial goes into Q naught stage. Okay. Okay, goes to Q naught stage. This part goes to Q naught stage. Okay. So it's quite difficult to understand this one, but you can refer to your textbook, yeah? It's more explanation in there. Okay, so now we stop for a while. Let's say we take like 10 minutes, okay, break. You can make a coffee, refresh yourself. Okay, 10 minutes, ya. Tu pukul 10, 20, 10 minit, 10:34. Masuk balik, ya. Okay, apa dia? Yang mana? Inhibit. Inhibit ni dia tengok dekat bila ni kat sini ni. Okey, kat sini. Yang ni dah habis dah. Okay. Ni dah habis kan? Ni dekat sini dah, bukan dekat clock. This is clock. Clock still high lagi kat sini. Okay, clock still high. But this is low. Low and both low. Dia tak boleh both low. Bila dia mesti one high, one low. Sebab because dia kata when S0 is high, okay, it shift to the right. When S1 is high, it will shift to the left. Tapi yang ini low. Faham tak? S0 high, S1 low, okay, shift to the right. When S0 low, S1 is high, shift to the left. Now at this point, both are low. So this part is ini bit. Stop already. Ini for data input, serial data input. Okay, this is how the serial data input goes. Kita tak pakai ni actually kan? Kita use this 1010 because this is for parallel. Kita design for parallel input, parallel out, right? Okay, so when we load, it load okay inside here. Yang ini dia kata if you use here serial shift right serial, when you have data here, it goes to the queue not here. Okay. If we use this one, okay, it goes straight to Q3. Okay, as shift left ni, serial. Then it goes to Q3. Okay. Ya, ada nak cakap apa-apa dengan saya? Nak tanya? Ada nak? Yelah, kelas tak pukul 11.30, okey lah kan? Okay. Okay, so everybody is here? Why everybody very quiet? Are you sleeping? Aiman? Where are you, Aiman?
Yeah, I am, Doktor.
Buka video, saya nak tengok muka awak. Semua buka. Saya nak tengok muka awak. Entah ada ke tak? Akasha mana Akasha? Okey. Aminah?
Ya, Doktor.
Mana buka muka awak? Pergi make up cepat, pergi make up. Okey, Amir Sufi. Amir Sufi ada tak?
Ada. Sekejap.
Amirun Fahim. Mana Amirun Fahim?
Ada Doktor, ada.
Okey, lagi Farhanani.
Ada Doktor.
Ada Farhanani sebab bila saya duk bercakap je, duk cerita je.
Ada Doktor.
Senyap sunyi je. Awak ada ke? Tak ada ke? Tidur ke? Tergolek ke? Hasif Mahathir.
Ada.
Irdina.
Ada Doktor.
Ya Doktor.
Muhammad Anas.
Ya, Doktor.
Okey, Seri dah live dah. Kenapa Seri? Muhammad Amirul.
Ada, Doktor, ada.
Muhammad Faidi.
Ada Doktor.
Okey, Muhammad Hafiz.
Ada Doktor.
Lagi Haziq.
Ada Doktor. Ada Doktor.
Okey. Muhammad Haziq Izzuddin.
Ada Doktor.
Muhammad Imran.
Ada Doktor.
Mana? Muhammad Izzat.
Ada, Doktor.
Muhammad Najib.
Ada, Doktor.
Okey. Ni Akif.
Ada, Doktor.
Okey. Nur Khairina.
Ada
Mana
Doktor.
Nur Khairina?
Ada.
Mana muka awak? Nur Syamimi. Mana muka awak? Khairina.
Sekejap Doktor.
Nurin Natasha mana?
Ada, Doktor.
Mana Nurin Natasha? Nurul Adlina.
Ada
Muka
Doktor.
mana? Muka mana?
Sekejap.
Safwat. Mana Safwat? Seri? Komputer okey tak Seri?
Ada. Sorry Doktor, komputer saya tak elok.
Shisilia?
Itu saya.
Muka mana? Tan?
Yes, Doktor.
Okey. Wan Adriana? Wan Adriana mana? Wan?
Ada nanti Doktor ada.
Si Syida tak tunjuk lagi muka awak? Wan Nur Adlin? And you?
Hai Doktor.
Okay. So now holiday doesn't mean anything anymore because you stay home all the time. Am I right? Okay. So you are still in campus or at your hometown? I heard that student being compound. The student being compound 29 student. Is it true?
In Kosas, Doktor.
Ada yang kena ni ke? Kena saman?
Doktor, but the people that are being compound are at Kosas, 29 of the students because they are playing basketball at the court, gather together.
Oh. So not you Not in
no.
college. Okay, good.
No, me safe.
Okay. How much they have to pay? 2,000 or one?
1,000 each, so total 29,000.
Wow. Kesiannya. So dia orang bayar lah.
Diorang kenalah bayar, tapi saya tak pasti lah kalau diorang dapat permohonan untuk kurangkan, tak pasti lah. Tapi kalau ikut kompon yang diorang dikenakan, 1,000 lah masing-masing.
Okay. That's what I heard because poli datang every day or alternate day. They check.
Dia random sebenarnya doktor. Dia macam kalau dia nak check, dia check. Macam tu lah.
Itulah pasal sebab saya dengar sampai lab pun dia pergi tengok tau. Okay. Jangan dia masuk bilik college pula dah lah. Okay. So since saya nak letakkan video ni. Tengok comparator because this will be in your test also. Okay. So make sure you study for a test.
This is Jim Pytel from Columbia Gorge Community College. This is Digital Electronics 1. This lecture is entitled Comparators. Comparators are another one of our common functions of combinational logic, and in its most basic form, all a comparator does is determine if two numbers are equal to each other.
Can you hear it?
Not equal to each other, they're obviously unequal.
Okay.
You can extend that inequality to something being greater than or something being less than. Again, in its most basic form, it's testing if two numbers are equal. And if we go back to some of our more basic logic gates, think of the description of equality, if it's the same or if it's different. Think about those logic gates. Which logic gates test if something's same or different? And those two gates are the exclusive OR and the exclusive NOR. And there's our description of the exclusive OR. High output if inputs are different, exclusive NOR. High output if inputs are the same. Okay, so it depends whether you want a sourcing or a sinking output, either an active low or an active high output. So for the example of an exclusive NOR, what I'm going to do is just put number A on there and number B on there. When they're equal, they're the same. So we'll output a high if A and B are the same. Now, we can't necessarily just limit ourselves to 1-bit numbers. I want to test for equality on a 2-bit number, 3-bit number, 4-bit number, so on and so forth. Think about equality if everything is the same. So what you're going to do is you're going to test every single bit position from the LSB all the way to the MSB. And if all of them are the same, the whole numbers are equal. So let's say A is now a 4-bit number going from A3 to A0, and B is a 4-bit number, B3 to B0, MSB to LSB. What I'm going to do is going to test every single bit position, and if all of them are equal, I should output a high if they're all the same. So how would you think you would do that? So using some of our basic gates. Well, obviously you're going to use an exclusive NOR, okay, because we want an active high over in this case. How do I synthesize all these? Well, they all have to be the same. Think about an AND gate. Okay, so the function would look something like this. Okay, so what it has here is our A inputs, MSB to LSB, and then our B inputs, MSB to LSB. And what's happening here is the MSB is compared, the next one down is compared, the next one down is compared, the LSB is compared. And what's going to happen if every single one of those bit positions are in fact equal? They're sending a 1 to that individual AND gate, and it's saying a 1 there. So let's just compare the number 1010 with 1010, that being A3 to A0, B3 to B0. Obviously, you're going to place 1 0, 1 0, 1 0, 1 0, 1 0. Take the MSB, they're the same, it's a 1 0 0, they're the same, it's a 1 1 1, they're the same, 1 0 0, the same, 1. We get those all ones routed to that single AND gate at the end, and obviously they're equal. Now, go ahead and change that bit position right there in the A LSB. What happens here is all the other AND gates, all the other exclusive NOR gates remain the same. Those outputs with the exception of this one. It is now supplying a 0 because it is not equal. The LSB is not equal. So it's setting a 0, and that AND gate is receiving 1110. The output of an AND gate is high when all inputs are high, all inputs are not high. A does not equal being sent. It's telling you that there is an inequality in there. Now, the point comes in, which way is it? Is it higher or less than? Is it greater than or less than? So the inequality can take two forms. number A can be larger than number B, or number A can be smaller than B. So it sounds like we have three outputs. We've got two inputs. And when I say two, I'm putting a quotation mark about that because A can take the form of a multi-bit number, so can B. So I've got A inputs and B inputs to a comparator. And it's obviously producing an A equals B out. If they're equal, it's going to go ahead and signify that as a high. But there are two other possible occurrences. A could be greater than B. A could be less than B. And my question to you before we even go into the next step here, these outputs here, the three outputs, can there ever exist a time when two or more of those are true? And the answer is no, never. You're wrong. Because A cannot equal B and simultaneously be greater than B. Does that make sense? Okay, 5 can equal 5, but 5 can never be greater than 5, or 5 can never be less than 5. Example, 6 can always be greater than 3, but 6 can't equal 3, and 6 can't be less than 3. What I'm saying is these three outputs, only one can be true at a time. Three outputs, only one of which can be true at any time. And I'm saying two quotation mark inputs because A and B can take a multi-bit form. It can be a 1-bit comparator. It can be a 2-bit comparator, 4-bit comparator, 8-bit comparator, and I'm going to put a plus behind that, 2 plus inputs, because we'll see when we go into cascading these things, i.e. taking a large bit stream and comparing them. I can potentially pass information from a higher or a lower order to a higher order, very similar to what we've done in our adder discussions. Basically a structural approach, letting ourselves do a structural approach and cascading. Think about a waterfall, a cascade. It's going from one level to the next level to the next level. In this particular case, what we're going to do is we're going to compare bit positions from, let me just think about how numbers are organized, the MSB. If A3, let's use this as an example, A3, A2, A1, A0, and its number B3 is being compared with B2, B1, B0, regardless of the value of these lower orders. What if A had a 1? A3 had a 1 and B3 had a 0, regardless of what those numbers are. We're talking about these numbers here. Which is bigger? Okay, it's pretty obvious. A is a bigger number because that is the MSB. So there's a relation between those higher order and those lower orders. But now let's say, for example, if our MSBs are equal, we'll go on to the next one. So we're doing successive comparison. If we've not determined if one is greater or less than using the MSB, step down to the next one. And let's say that those are both equal. We've got an equality. Let's go ahead and go down to the next one for an inequality. Which one is greater now, regardless of the value of A0? It's pretty obvious. B is greater. So it sounds like there's going to be a relationship that's forming. Brief divergence, though. We did, in a previous take-home assignment, develop the K-map expression for a 2-bit comparator. We had as number A1, A0 being fed into a comparator. We developed the expressions for it. A equals B, A is greater than B, A is less than B. And I'm not going to give you the answer because, again, it's a take-home assignment. I know some of you guys are probably advanced in the lecture to go ahead and see what's going on, but it's super easy to set up. I'm just going to show you the setup for this. A1, A0, B1, B0. Those are my inputs. Exhaust all possible combinations of inputs. What are my outputs? A is greater than B. A is equal to B. A is less than B. When A is greater than B, put a 1 there. All the other ones are obviously 0 because A can only be greater than B in that particular circumstance. If A is in fact equal to B, put a 1 there. If A is less than B, obviously put a 1 there. Just basically, it's just exhaust all possible combinations of input. Think about it for this one. Think about it for that one. Think about it for this one. Determine the appropriate outputs. What do you do with those things once you've developed the truth table? Take the truth table, put it in a K-map, a 4-variable K-map for A is greater than B, entirely separate. Take that truth table for this column, put it in a K-map for A equals B, come up with a minimum logic expression. Finally, you guessed it, move on to that next column for A is less than B, put it in a K-map and come up with an expression for A is less than B. I'm not going to give you the answer for this. We have already gone over it in lab. This is a take-home exercise, but you should be able to do this. And hopefully you're going to come up with the same answer that we came up with in lab there for the review. The point being is that there are 3 separate outputs based off these 4 input combinations. That is a way to do a comparator. It's a way to do a 2-bit comparator. What we find to kind of run up against the wall here is this, the ability to do this in a K-map. Well, why not do a 3-bit comparison? That's a 6 variable K-map. Things are going to get a little bit more complicated, okay? I might be able to come up with a structural approach that might be able to help me out where a single bit comparator is being used to pass information back and forth. Before we go into that, I do want to do this concept of cascading. Like I said previously, there are 2 quotation mark plus inputs. Okay, and this concept of cascading is I can have lower order comparators passing information up to the next higher order comparator. The higher order comparator takes precedence, but if there's an equality shown in that higher order comparator, it's got to take information from the lower. Okay, so what I'm going to do is just draw a simple diagram of what I'm talking about here. Okay, so in its simplest form here, we've got our comparator with 2 inputs, A and B, and it's got its 3 outputs. Let's just put the number MSB to LSB 1 1 0 1 with 0 1 1 1. What do the outputs look like? Well, A is bigger than B, so it's got 1 0 0. But now, what if A was part of another number? What if B was part of another number? I've got to I've got to find a way to pass information between 2 comparators. Okay, if you can imagine, this is the inside and that's the outside. Check this out. What we're going to add is something to the inside. Namely, A is greater than B, A is equal to B, A is less than B inputs from a previous stage. So, and then what's neat about this here is this right here could be the outputs for that stage be fed to another stage. So if you can imagine here, this is A3 to A0, and the guy below is B3 to B0. In reality, let's pretend that they're part of a 8-bit number combination. What are those? A7 to A4 and B7 to B4. What we're going to do is if that's the low order, what we'll do is have the high order comparator right next door. Now all I do is I route A7 to A4 to that one, B7 to B4 on that one. And this output goes to that one's input, this output goes to that one's input. And now what it's doing is it's saying, okay, in this particular circumstance, A is greater than B, A is not equal to B, A is not less than B. And then it's passing that information up to the high order. Now the higher order, let's say in the case of equality, let's say they're all quadruple zeros. Ordinarily, if there was no feeding inputs, it would say, oh, they're equal. Basically, it is now relying upon the logic for the lower order adder. I'm equal. At this point, go ahead and check my inputs, namely these here. Is anything below me greater than, equal than, or less than before it makes its final decision? And what it's seeing is it's seeing that A is greater than B. It's going to go ahead and signify that. The question remains is, what do I put here on the low order comparator? What are my inputs? Well, if it really is A3 to A0 and B3 to B0, implying that that is the lowest portion of it, that is the LSB. A0 and B0 are in fact the LSB. What's the previous relationship? Well, they're equal. What I need to do is put a 0 there, put a 0 there, and put a 1 there. Okay, so your lower order comparator on its input, the A equals B input, will always be tied to 1. And what it's going to do is take its output being fed to the higher order or the next higher order. If you're going to do like a 12-bit number or 16-bit number, its output number being fed to the next highest stages inputs. And now it can make that comparison. So let's use this exact same relationship when we came up here. I'm just going to put some different numbers on here. Let's see if you can think how this thing works. Okay, so we've got A7 to A0 taking these values. Now we've got B7 to B0 taking these values. Let's use the one on the left as our low order inputs. So what I'm going to do is I'm going to take A3 to A0, put them on our A inputs, B3 to B0, put them on our B inputs. What am I going to do on the low order equality and inequality inputs? Well, the one previous to the one lower than the LSB was 0, 0, 1. Got to do something with that low order inputs first. What does my low order outputs look like? Well, this is being sent to my low order, that being sent to my low order. I've got a case of quality. And now what I'm going to do is take those outputs, these are the next stage's inputs, and now it's going to make the decision. It's basically the low order saying, hey, everything on my end, they're equal. I can't make a decision if this is an 8-bit number. It's up to you. The higher order adder. It's almost like we're in the situation right there. What are my inputs for that higher order adder? What's 0, 1, 0? Saying everything below me is equal, you get to make the decision. Go ahead and tie A7 through A4, 0001, 0010. Which one is bigger, 1 or 2? Well, to me, binary 2 is bigger. So B is bigger, and that is our final output. The number B7 through B0 is greater than A7 through A0. So it's this concept of cascading. So let's talk about 1-bit comparators. We talked about having 3 inputs in there. You could also kind of streamline this. You can make 4 inputs for 1-bit comparator. One would think that I'm going to have to do A and B, and I'm going to have to do it. A is greater than B, A is equal to B, A is less than B inputs to come up with A is greater than B, A is equal to B, A is less than B outputs. So it's 5 ins, 3 outs. One would think that you'd have to do that for a single bit comparator. And then if I wanted to use a structural approach in VHDL, I would have to take this model and hook it up with another one next to it. And if I wanted to make a 3-bit comparator, hook up another one of those. You kind of trick this thing. You don't necessarily need that A equals B input or output, because if that's 0 and that's 0, what is A equals B? Well, it's equal to B. Because you're using that property of 3 outputs, only one can be true. If that's false and that's false, obviously A equals B. That being said, your final comparator in the MSB position does have to have that, okay? Because you want that 3 final outputs. So what you might look, if you try this in a structural approach, is something like this. So you want to make a 1-bit comparator. There you go. You've got 2 numbers, A0 and B0, and it's taking your 3 outputs. A is greater than B, A is equal to B, A is less than B on the left-hand side, and it's got 2 inputs. A is greater than B, A is less than B on the right-hand side, and all I'm going to do is say 0 on both of those. So what I'm doing here, what I've gained from this, I can do a 4-variable K-NAP expression to come up with the logical expression for this guy, the logical expression for this guy, and the logical expression for this guy. Okay, now here's where the magic comes in when you use the structural approach. You want to go make a 2-bit comparator? Just take that single 1-bit comparator and hook it up in the following fashion. Just don't hook up that output. It's unused in this particular case. All this comparator, all the next highest order comparator needs to know, namely this one here, all it needs to know is if it's greater than or less than. And again, what do you think you're going to do to make the 3-bit comparator? Obviously, just add another one. There you go. Then make the 4-bit comparator. Let's say that's where we want to go ahead and end. And now here is my final output for A is greater than B. Here is my final output for A is less than B. And then, again, looking from the outside world, here is my output for A equals B. What I'm going to do is basically put this thing in a larger box. And there you go. I've created a 4-bit comparator where I've got 3 outputs. A is greater than B, A is equal to B, A is less than B. And I've got my 4 inputs for 2 numbers. So let's say I've got 2 4-bit inputs, and then I've got 2 cascading inputs that I could use. Okay, if I wanted to create an 8-bit comparator, what I could use is the component instantiation of a 4-bit comparator. Okay, so this is another example of how that structural approach can you save some serious time and money. This is the only way to implement a comparator. The answer is no, because it's just the structural description. There are some pretty powerful behavioral descriptions that we can implement a little bit later on, which we'll show you guys in the lab when later lectures. This kind of concludes for comparators here. Let's move on to our next common function, combinational logic.
Okay, finish. Hello. Okay. Ni dah tengok kan yang ni? This one dah kan? How to design filter. Counter. Ini dah tengok ke belum? Dah kan?
Dah tengok.
Okay, dah cukup. Kita buat quiz.
Oh good.
Sekejap lah, mana quiz saya letak kat mana? Okay. Okay, now take piece of paper, write your name, metric number and quiz number. Quiz number apa? 8, I think. Okay, dah ready? Okay, ready Alright, quiz number 8. Ikut suka lah, tapi saya nak jawapan. Upload dekat Putra Blast. Awak jangan bagi jawapan pula kat dia orang. Okay, ready? Finish? What about others? Finish? Yeah. Okay, finish? Okay, if you have finished then yes. No, upload the answer in Putra Blast.
Doctor,
Yes.
doctor, this is quiz 8 ah?
Yes, quiz 8.
Okay, okay. So,
Putra Blast goes to Putra Blast not later than 11:30. And don't forget to take your attendance. Okay, so continue on Wednesday. We have a few more slides. I can finish on Wednesday. Okay. Okay, see you on Wednesday. One student is missing. Who is missing here? Siapa yang dah left? Other one is missing. Oh, Pradeep. I don't see Pradeep. Where is Pradeep? Does he know that we have class today? Okay. Okay, so see you next Wednesday. Bye.
Thank you, Doctor.